So the next reaction I want to discuss is the acid-base neutralization reaction, in which essentially an acid reacts with a base to yield water and an ionic compound, which is referred to as salt. A lot of times people refer to, when we use the word salt, people refer to it as sodium chloride, like NaCl. But realize you could have any salt. You could have CuSO4, that too is a salt, which would have gotten generated from H2SO4 and CuOH whole twice. So CuOH whole twice plus H2SO4. And now when you switch the cationic and the anionic ionic partners, you're going to end up with CuSO4 plus 2 molecules of water. I'm going to write water as HOH just for the sake of simplicity here. But realize this too is a neutralization reaction where your base is cupric hydroxide or copper 2 hydroxide, which reacts with the acid H2SO4 to give copper 2 sulfate. So any acid-base neutralization which will involve an acid, a base, and it is going to generate essentially a salt and water. So the generation of water is the driving force for this reaction. Again, realize that it is a type of an acid-base neutralization reaction, and the reason why we call it an acid-base neutralization reaction again is the generation of salt and water. So don't just look for water, but look for salt and water as your products if you have to identify a specific reaction. But this is a double replacement reaction also, and the reason why we say so is because the cationic end, which is a positive end, reacts with the anionic end of the other to give you a new product, in this case that happens to be water. So again, I have provided the address of this YouTube video where I look at both the double replacement reactions, the precipitation and the acid-base neutralization reaction, and kind of try to differentiate between the two. In case of precipitation reaction, realize that we are going to start with two clear solutions, and when you mix them together, some solid will get generated. Whereas in case of a acid-base neutralization, one of your starting materials has to be an acid, and an acid always reacts with a base to generate salt and water. So simply looking at the kind of starting materials, kind of products you're getting, you would be able to identify a precipitation reaction and be able to distinguish that from an acid-base neutralization reaction, because in this case more than 99% of the time when you see the H2O with liquid, you should be able to identify that. But again, I want to bring to your notice, it's not just the formation of water but salt and water that you should think about, because, and the reason why I say that is you could have something like methane reacting with oxygen, which will give you CO2 and water. So just formation of water is not really the cause for acid-base neutralization reaction. The starting materials are equally important, whether those are acids or bases or what. The second example that I gave you, the methane with oxidizing with oxygen, that is specifically like a combustion reaction, a redox reaction, so that's different. Going forward, an acid can be of three different kinds, and actually those of you who have to take general chemistry 2 and then go over to organic as well, we are going to take a look at that in much more detail. But for the purpose of this class, we are going to focus on the older Arrhenius acid, as well as what are called as Bronsted and Lowry acids. Arrhenius acids are those which in water dissociate to generate hydrogen ions. So you are going to see H+. So as an example, you can perhaps envision that you could have HCl, HNO3, H2SO4. All of these do have the capacity to generate the proton, the H+, and so these are acidic Arrhenius acids. A substance that dissociates in or reacts with water and forms hydroxide, that would be called as an Arrhenius base. So something like NaOH, something like KOH, something like CaOH whole twice. These were all classified as Arrhenius bases by this Swedish chemist. This was done maybe about like 100 years ago or so. More than that, maybe 150. This typical Arrhenius acid and base concept, however, suffered a major flaw. As science was developing, there was a problem, and the problem was that this was a very limited classification method. And first things first, your solution had to be an aqueous solution. And the other problem was that it did not account for a lot of substances like organic amines or even ammonia for that matter. These were thought to have a basic pH. They were considered basic in terms of their properties. They were exhibiting properties of bases, but really there was no way to prove it, because if you look at the formula NH3, you know, how would it generate OH? There is no OH to give away, and so there was a problem. And so it was not until 1923 when Bronsted and Lowry actually worked on this problem, and they actually came up with a different kind of classification, and we are going to discuss that shortly. So Bronsted acids were defined as those compounds which can donate protons to another substance. So let's just write that somewhere. Proton donor is an acid. Proton acceptor is a base. So now the question was that if you treat HA, which is a proton donor, which is acidic, and you treat that with B, which is proton acceptor, what do you end up with? And in this case, you end up with a BH plus, and the A is given away as a negative. So let's take a quick look at this. HA has dissociated to get into H plus and A minus, so that is the proton donor, that is my acid. Now acid always reacts with a base. What becomes of the acid after losing the proton, so what becomes of the acid is what is called as the conjugate base. On the other hand, what becomes of the base upon the loss of acceptance of the proton is going to be called as a conjugate acid. So at any given point of time, there will be two conjugate acid base pairs that will be present in the system. Let me write that somewhere. There will be two conjugate acid base pairs in the system. And if you really think about, you know, the two possibilities, you would say this is HAA minus, that's one system. The other system is BH plus, that is going to be the second system. And this is how you can identify and classify, characterize these two systems. So let's see if we can apply that on this question. The question here is, for the following reactions, label the acid, base, conjugate acid, and conjugate base. So really speaking, you have to just look for what is the proton donor, what is the proton acceptor, and make your call from there. So if you compare the first reaction, if you compare the various different reagents and products, and you compare what you have for acetic acid and what it becomes, realize that it has a proton less. That means it must have donated the proton. This must be a proton donor. That means that this must be the acid. And if acetic acid is the acid, that means water is going to be the base. Now, what becomes of water, the base, upon acceptance of that proton, the hydronium ion, we are going to call that a conjugated or conjugate acid. And what remains of the acetic acid is going to be the conjugate base. Realize in this, an acid is either something which can donate a proton or something which is positively charged, whereas a base is something which is neutral, in which case it will have lone pair of electrons such as water, or it will have a negative charge. So you can perhaps remember in your head that negative charges are usually conjugate bases, positive charges are usually conjugate acids. But of course, we are going to discuss this in a greater detail in general chemistry too. Let's take a look at the second reaction. We have ammonia, which is becoming ammonium. So NH3 became NH4. That must have occurred by the acceptance of a proton. That means this must be a base, and that would make water an acid. So ammonium ion is going to be the conjugate acid, and the hydroxide that gets generated from water is going to be the conjugate base. Again, notice the negative charge on hydroxide, which is a base, and a positive charge on the ammonium ion, which is making it a conjugate acid. Okay, let's go forward. The question here is, which of the following is a Bronsted-Lowry base but not an Arrhenius base? Recall, Arrhenius base needs to be a hydroxide donor. Bronsted-Lowry base is a proton acceptor. Now, if you think about it, ammonia is a Bronsted and Lowry base because it's able to accept protons. However, it doesn't have any, OHs to donate, and so it can't be Arrhenius acid. So the correct choice in this case is ammonia. All right, going forward. Acids and bases can be classified as strong acid, weak acid, strong base, or weak bases depending on the extent of ionization that takes place in them. Now, a strong acid almost completely dissociates in water. And so good examples for these will be HCl, H2SO4, HNO3, HClO4, which is perchloric acid, HI, HBr, and the likes of those. Weak acids, on the other hand, do not dissociate well in water. Good examples will be hydrofluoric acid, hydrocyanic acid, acetic acid. Strong bases, on the other hand, will be something like metal hydroxide, like sodium hydroxide, NaOH, KOH, CaOH whole twice, and the likes of those. On the other hand, a weak base, such as ammonia, will not dissociate well in water. So, for instance, ammonia does not give you OH negative, first of all. So a good example here will be NH3. And this chart just basically describes that as well. Perchloric acid is one of the most acidic acids that mankind knows. Hydrobromic, hydrochloric, hydroiodic, all of those. Usually anything ending as an ic acid is a stronger acid as compared to its us acid. So for example, recall from chapter 2, sulfurous and sulfuric. Sulfurous will be considered weak, sulfuric will be considered strong. But of course, if you have something like phosphoric acid, hydrofluoric, acetic, even though they end in an IC, those can be weak acids because that's the only possible format that they form. So the rule that I was saying that the us acids are weak and the ic acids, it's only comparative for that. So you have to consider, you have to take it with a pinch of salt here, that you are looking at HNO2 versus HNO3. So nitric acid is going to be a stronger acid than nitrous acid. That's what I'm trying to tell you here. Likewise, sodium